Hello and welcome everybody. My name is Michal, and today we will go through some of the latest questions from radio navigation, and I'll try to give you some tips as to how to answer the questions and what to look for in the actual exams, and we'll go a bit deeper into the topics and the possible answers. So all the questions that you'll see in this video, they are the latest questions seen across all EASA authorities in the last 30 days. So if you're preparing for the exams, it will be a great refresher, and if you're just here to see what radio navigation is about and what's latest in EASA, then it's also a good place to be. So without any further ado, let's just jump into question number 1 out of 8. So which of the following codes is suitable for a transponder? So this is a slightly tricky question, and I say this because there is one number that you'll probably remember for your exams, which is 4096. And this is actually the amount of all possible transponder code combinations. But this is not suitable for a transponder because transponders work in the octal system, meaning the numbers that are available range from 0 to 7. So we have 8 numbers in total that we can use, but the 7 is the max. So any number with 9 or 8 in it is not suitable for a transponder, meaning 4096, although right answer for some other questions will be incorrect here. And of course, 5600 will be the correct number for a transponder code. And lastly, remember just a few tips about the transponders. The transponders work on the interrogation and response model, meaning there is an interrogating station which sends a signal to the transponder on the frequency of 1030 megahertz, and then there is a response from the aircraft transponder at 60 hertz more, 1090 hertz, the response signal. And these are very useful. There are 3 key types in aviation in the aircraft. So there are alpha type transponders, which only transmit the basic information about what the aircraft is. So the identification. Then we have the Charlie transponders, which can give you some more information, and more specifically, they report altitudes in the increments of 100 feet. And then lastly, the most advanced ones, so Sierra transponders, and these can transmit, apart from other information, the altitude. They have altitude reports in increments of 25 feet, and actually these are the transponders that are required for TCAS to operate and in order to send resolution advisories to both aircraft if they are on intercepting courses. So this is the transponder that you need, and all the other information that you might hear from that ATC uses will be sent via the ADS-B or ADS-C. Just for your future reference, this is something that we could dive a bit deeper during the instrumentation subjects. However, remember that 4096 is are the all combinations, and 5600 in this case will be the only correct code suitable for a transponder. So for question number 2, a GNSS approach may achieve a lower minima by using a ground station to transmit correction signals for a small defined geographical area. An example of such approach is. So this is an interesting question, a very practical one as well. But if you understand the general idea, it becomes really, really simple. Of course, LNAV VNAV, this is an RNP approach. So we have laterally managed guidance using the GPS, and in most cases, VNAV is barometrically. VNAV baro uses barometric information for vertical guidance. There are some cases where you can use also the GPS for VNAV, however, you can only always fly to the baro minima. In that case, of course, a GNSS approach that allows us to fly to Cat 1, 2, or 3 will be GLS, which is the only one considered a precision approach per se. In this case, as LNAV VNAV is a 3D approach. However, this approach is type alpha from the new classification, meaning a minima above 250 feet, rather than type Bravo, which is ILS or GLS. Lastly, APV is not really a type of an approach. This is a classification. So of course, in ICAO Annex 6, you can read all about the precision, non-precision approaches. However, EASA, because these annexes are not often updated, has decided to differentiate the approaches in a bit different way. So differentiate them 2D, 3D, type Alpha, type Bravo, and APV was somehow of a compromise between non-precision and precision, as these approaches are simply with vertical guidance added, but do not have any ground navigates to take information from, which is vital for precision approaches that go to Cat 1, 2, or 3 minima. Here, remember that in Europe, we mainly use ILSs for Cat 2 and Cat 3 approaches, as well as Cat 1. The only GPS approach that can be really flown down to Cat 1 minima is the LPV, but it's still not necessarily considered precision unless you're in the exams. In the exams, you need to consider LPV, a precision approach. In that case, a GLS approach will be the only correct answer here for the GNSS approach that can achieve lower minima than standard. For question number 3, a student pilot has just learned that meteorological information for aircraft en route on long-haul flights is sent by radio. What kind of radio receiver is needed to receive this information? So generally speaking, in order to receive meteorological information, we will be using VORs, broadcast VORs specifically, and they send us the ATIS in most cases. However, the keyword here is long-haul flight, and in long-haul flights, we need to use frequencies in the lower frequency band, and in this case it will be an HF, and the HF frequencies allow us to transmit volnets, which are basically en route METAR, staffs, and SIGMET information sent to an aircraft on a single sideband receivers. And we'll get to single sideband receivers in the next question. However, these allow for very good efficiency when it comes to transfer of information across long distances, and they are strictly linked to HF frequencies. However, remember that if it's not a long-haul flight, a broadcast VOR, meaning VHF receiver, will most cases be the most appropriate answer. So now going into question number 4, again, a very practical and useful question here. So in order to be considered established on an NDB approach, the deflection or correction or the bearing must be less than. And this is a very practical question and a very relevant one when it comes to the instrument rating theory and the practical side of your instrument rating. And in order to be considered on an NDB approach, the bearing pointer must be within 5 degrees from the required course, and this will be the correct answer. For the VOR approaches and the localizer approaches and any other type of approaches, you are considered established when you are within half-scale deflection. And being established means that you are clear to continue the procedure. So in most cases, you are clear to descend because now the obstacle clearance is guaranteed by the procedure. If you're not established on the said radial, bearing, or course, in that case, the obstacle clearance, terrain clearance may not be guaranteed. This is why it's very, very important to always be established on your course, bearing, localizer, or radial before you start the descents and before you start following certain procedure. This is why this question is so vital, and you'll come across it very many times once starting the flying phase of your instrument rating, I am sure. For question number 5, which of the following is the correct frequency band, propagation path, and frequency range for single sideband communications? So as we have discussed previously, the single sideband is most important in terms of HF frequency bands. Of course, the single sideband essentially means that when we have a carrier wave for an HF frequency, it has a mirrored image on the bottom of the amplitude. So a single sideband communication, which is used in both one-way volnets and two-way communication, cuts down one of them. So you still hear exactly the same thing. However, you decrease the energy required to receive and send these signals by half, increasing the efficiency, but also the range and the clarity of the communications. The HF waves are used for this communication, and because they have greatly bigger range than VHF, which is used more commonly when flying inland. So HF is the preferred one when it comes to long haul communication because it propagates as both surface, or more accurately ground, and sky waves. So VHF will propagate mainly as ground waves, a line of sight, and they're limited to around 150 to 200 nautical miles depending on the day and the atmospheric conditions. However, the VHF, because it has a lower frequency, is able to bounce out of the ionosphere and then return back, increasing the range up to 800 to even 1000 nautical miles in some cases. So remember for your exams that VHF will be the line of sight. It's also used most often for the comms when flying inland. HF will be the preferred communication band when flying long haul because it's increased distance and frequency is able to jump or bounce out of the ionosphere. For question number 6, an aircraft is on radial 120 with a magnetic heading of 300 degrees. The track selector, the OBS, reads 330. The indication on the course deviation indicator, CDI, are fly. So now, what is happening? And in these questions, I always recommend to think about them as if you were thinking about the reciprocals. Generally, when it comes to the OBS, so instruments like this one, when you're flying from the VOR, your selected course will be your radial, and when you're flying to the VOR, the reciprocal of selected course will be your radial. In this case, when we are flying on a magnetic heading of 300 and the radial is 120, then it's really easy because we are working with reciprocals already. However, if the track selector reads 330, that means that our radial selected will be again the reciprocal, which in this case is 150. So now, since we are on radial 120 and we should be on radial 150 in order to have radial 330 after passing over the VOR, we of course need to fly to the left because radial 120 is to the right of radial 150. And since we are flying on a heading of 300 with the selected course of on being on radial 120, meaning we're flying towards the station, towards the VOR. So the correct answer here will be left 2, with 2 showing on the instrument. And now for question number 7. So this question is relatively straightforward. However, a good tip that I could give you here in this particular case is to read the introduction part of your GSPRM book. So if you own the GSPRM book, if you have already studied flight navigation, reading the introduction will greatly help you in case of these questions, especially when it comes to deciding what the particular nomenclature and signs are showing on a map. In this case, we need to find the identifier for the Pamplona VOR. So this is the image that we are working here with. And as you can see, this is a relatively straightforward question. However, there are some trucks you need to be careful. So of course, you can see in the green Pamplona, this is not a VOR, this is a Navate. However, this is an NDB. And you can see this by a 3-letter frequency, or you can just see this because of the icon in the middle with the dots showing. Of course, this is an NDB. And then we have also a second VOR here. So at the bottom, Pamplona South VOR, which can be easily confused with the Pamplona VOR in orange, which is what we're looking for, Papa November, with frequency 112.3. And sometimes you'll see a small d next to these. And in Jeppesen charts, the small d will refer to the DME, which is paired together with the VOR. However, in this case, 112.3 and the Morse code with the dot at the end, meaning this answer will be the correct one. And then for the last question that we have here today, so how many degrees does one localizer dot represent on a 5-dot HSI or CDI in the ILS mode? So of course, the localizer and the glide slope and the ILS, they will show you a slightly different deviations when it comes to 1 dot. The localizer is a bit less accurate than the glide slope. It will show you 2.5 degrees of deflection to either side, left or right. And the localizer will also have a greatly increased distance. It will have a distance range of 25 nautical miles at the 10 degrees left or right from the localizer, and then at 35 degrees at around 17 nautical miles. So the glide slope will have a range of about 10 nautical miles, 8 degrees left or right from the station. So as you can see, it has a much lesser range, but it will have a greater sensitivity because the ILS glide slope beam will show you the deflection of 0.7 degrees half scale, fully up or fully down. And in case of VOR, 1 dot on a 5-dot HSI will show you, of course, 0.5 degrees. For the glide slope, the answer would be 0.14 degrees, roughly. Also remember here that the ILS, it works on the principle of difference in depth modulation. So we have 2 lobes, one 150 Hertz, one at 90 Hertz, and the system or the receiver essentially measures the difference in modulations of these two. And when the difference is 0, that means that we are exactly in the middle of these 2 lobes, which means that we are either on the localizer or on the glide path. So this was everything that we have here for today. I know this was quite a lot of information, a little bit of an intense session with a lot of questions. However, I hope it was helpful. As always, if you have any questions, feel free to ask. I wish you all the best for the upcoming exams, and I hope to see you on the next video. So all the best, and bye-bye. Thank you for watching.